In this video, we're going to talk about graphical limits, and as we do these problems, we want to understand how graphical limits are similar, but yet different. How limits are similar yet different than just evaluating a function. So in these examples, we're going to look at six graphs, and in each of those, we're going to compute both the function value and the limit by looking at the graph. And we want to compare them. And this will help us to do a couple of things. It will help us to understand how to find limits graphically, and it'll also help us to understand the difference between the limit and a function value. So our first example here, we're graphing the equation y equals x squared plus 2x. So I have that graph. And now as I look at this graph here, I want to consider what happens as x approaches the number that I've marked here is 2. And you can see on the graph here that as I squeeze in towards 2, right, the y value is squeezing in towards 8. So the limit as x approaches 2 here would actually just be 8. The limit would actually just be 8. Now, as far as what is the function value, well, if we go to x equals 2, right there, and we look up to the graph, we can see that it is also 8. So in this particular example, both the limit and the function value approach the same amount. And this is very much like that first numerical example we looked at when we were talking about a polynomial. So there are going to be times when the limit and the function value are the same. In fact, one of the big ideas of our next section is going to be developing a set of criteria for when that's going to happen, because if the limit and the function value are the same, then taking the limit just comes down to evaluating the function, which is easy. But we're also going to look at those other cases where it's not the case. So let's consider a second example here. In this second example, we're looking at a rational function here. Y equals x squared. Well, you can see this, so I'll rewrite it. X squared plus x minus 12 all divided by x minus 3. Okay. All divided by x minus 3. And its graph actually turns out to be a straight line. But like most graphing devices, there is a bit of a problem. The original thing there is undefined at x equals 3. And that's because we would be dividing by 0. And so that's undefined. But if we look at as we approach 3, on the other hand, you can see on the graph that we are in fact approaching 7. So the limit as x approaches 3, that is actually going to be 7. But the function value is actually not defined here. So here we have a limit, but we don't have a function value. This is very much like example number 2 that we did numerically, where we actually can't evaluate it, but the limit does settle in towards an actual number. Let's consider our third example now. In our third example, we're looking at a piecewise function, a function that's defined in pieces. The equation here is 4 minus the quantity x minus 1 squared, as long as x is not equal to 1, and 6 when x is equal to 1. So when I draw the graph, since the parabola shape isn't defined at x equals 1, when I come to the graph, I have to put in that open circle there. And then at x equals 1, it's equal to 6. That's why I've marked that up there. So now as we look at this problem, as we squeeze in towards 1 along the graph, we can see that we are in fact approaching 4. All right, the graph gets closer to the y value of 4 as we squeeze in towards x equals 1. Yet we know from reading the graph that the function value is 6. F of 1 is 6, because when x is 1, we use the bottom equation to get the answer. So that gives us an answer of x equals 6. So here we did have a limit, And we did have a function value, but in this particular case, those two things were not equal. Those two things were not equal. So we're going to stop here in this video. In the next video, we'll look at the other three possibilities for limits graphically, and how the limit can be different than the function value, although sometimes it can also be the same.